Hey guys, welcome to week 14. You are getting so close to being done, just 2 weeks left. So the last couple weeks in this semester we will talk about radical functions and solving radical equations. So today you're just getting, this activity just gets a feel of what radical functions look like and talking about where they're defined. So we start with this activity about a person in free fall, a person jumping out of an aircraft, and talking about when they should release the parachute and how long they travel versus certain times. So the first thing we had to do, they gave us this equation or this function, to use. They said that the distance that they will have traveled, for a certain time in the air is given by s equals 16t squared. So this is really just using gravity. This is not throwing something up with a certain velocity. This is just this person jumping out of the aircraft. So I filled it in, just plugging in each of those times and finding the corresponding distance. And the next thing I just did ahead of time was to just graph that. All things that you can do very easily, just plugging in and then plotting these values. So take a few minutes and fill those out and then catch up with the video. So now the skydiver needs to know how much time they have before they're activating the parachute. So they're jumping from a plane at 12,000 feet, so that's how far they're starting up high, and they have to activate it at 3,000 feet. So they really have to activate it. They have to activate it after 9,000 feet. They start at 12,000. At 3,000 feet, they have to activate it so that they'll be in motion for 9,000 feet before they activate it. So use this formula to determine how much time she'll have in free fall. So to go 9,000 feet, we're going to solve this for time. So we're going to solve it by dividing out to 16 first. So notice this is just a quadratic. I don't have to use quadratic formula because I don't have a linear t term. I can actually just get this t by itself by taking the square root. I'm not bothering with the plus or minus, although when we solve a quadratic and we take the square root, we do use plus or minus, but we know the time is only going to make sense to be positive here. So I'm only going to take that time. If I just divide that out, I end up getting 23.7. I want to put one little note over here on the side, it will come up later. If I am evaluating something like this by hand, now I just went on the calculator and divided that out and then took the square root. But I am able to actually take the square root of 9,000 and the square root of 16 separately and divide it after. So next, we're looking at solving this equation now for t for good, just before we did it for just one certain value. So now we're going to take this equation, s equals 16t squared, and we're going to solve it for t, for time, so that we can use it a little bit differently. So we're really going to do the same thing that we just did. We're going to divide out the 16. So divide out this 16. So I have so far s over 16 equals t squared. And then I'm going to take the square root of both sides. They're saying t is just positive, so I'm actually only looking for the positive one. So t is going to be the square root of s over 16. So I'm just going to go over here on the side and rewrite that using that fact that we just did. We could also say t equals the square root of s over square root of 16. And it helps me a little bit because then I can actually simplify to this. Or to this. Both of those are equally as good. This one right here and this one is right here. But by separating that radical into top and bottom, I was able to at least take the square root of 16. So this function and the original one that we started with right here, the s equals 16 t squared, are the same exact equations, just solved for a different variable. So now they're having us take the distances, plug distances in, and get out time. So we're just using it a little bit differently. So I went ahead and I plugged in each of these values right here. whoops, sorry about that. Each of these values right here in my table, I plugged them all in for S and got my corresponding time. Okay, and then I graphed it. Okay, so we're really going to look at the graphs of these together on what these two things look like. Okay, so our next step down here, so fill that out and catch up with me after that. How are the ordered pairs in these two tables related? So if you look at each ordered pair, like on the first table, we have the ordered pair 5, 400. And on this one, we have the ordered pair 400, 5. Okay, so how are they related? These two ordered pairs are reversed. You know, the x became the y became x. So functions that have their input and outputs reverse are what we call inverse functions. Okay, so it makes sense. A square and a square root, they kind of undo each other. They're inverses of each other. So that's why these two functions are inverses of each other. One had a square, one had a square root. Okay, so now we're looking at this same one that we just had. We had just found this function t equals 0.25 square root of x. Is somewhat limited because of the restriction placed on the variables t and s. Okay, so let's look at the function, same function, we're just calling it f of x now, 0.25 square root of x. And what is the domain? So we know we can only take the square root of positive numbers. So the domain of this is that x has to be greater than or equal to 0. In other words, to write that as 0 to infinity. So we can't use negative, although we can use 0. Next slide. Okay, and I did that ahead of time. Okay, it's really the same graph as that we had before because it was the same function. So if you look at this little green box, it's just saying that the domain of a function defined by a square root, a radical function, what's underneath the radical, which is what's called our radicand right here. This is called our radicand. It's not that x has to always stay positive. It's that the whole value under the radical has to stay positive. So you'll see they're giving you an example there where you have to determine what makes that 2x minus 10. So if that were under a radical, if I had a function like this, it's saying that x would have to stay 5 and above in order to keep that radical term positive. Okay, so let's look at a couple other ones. So let's consider the domain of each one of these. So, well, we know the original one. We just did that one before. X just has to stay greater than or equal to 0. But on this next one, let's think about what's going to make this stay positive. So if you're not sure, you would say, well, x plus 2 has to stay greater than or equal to 0. Which means x has to stay greater than or equal to negative 2. So that's my domain. As long as x is greater than or equal to negative 2, that term under the radical will stay positive. And then likewise, if I have h of x equals x minus square root of x minus 3, well, x minus 3 has got to stay greater than or equal to 0, which means x has to stay greater than or equal to 3. So 3 is the lowest value I can use in that one and keep that positive. Because think about it, you have to take each x and take away 3. You have to subtract 3. So 3, if I put a 3 in, that gives me a 0 out. Anything less than that, I'm going to start to get a negative out. Okay, so the next thing they're having us do here is to take those three functions that we just had, we were just looking at, and graph them on the same graph. So I did that. You can use the graphic calculator for that, and you're just trying to compare them. And we're looking for all these functions increasing or decreasing. So all three of these, all three, are increasing. Okay, determine the domain and range of functions defined by, okay, so that's all we're doing with those functions. So now we're looking at two different functions, f of x equals square root of x and negative. Okay, so both of these have a domain of x greater than or equal to 0. We can only plug things in there that are going to give us positive value, or that are where we can take the square root of positive value. So the domain is x greater than or equal to 0. Now the ranges are going to be a little bit different. So the range of f of x is y is going to be greater than or equal to 0. But the range, let me squeeze this over here, the range of the other one you're going to see, when we graph it especially, is, hold on, let me get rid of that, is y less than or equal to 0. That's going to give me like a bottom half of the graph. So look at these two graphs. The red one is the original one, and then the green one is the bottom half, is the one that has the negative in front of it. And you can see the range of that is everything lower than or equal to 0, because that opens what we would say down. So how would you obtain, like, what is the relationship between them? Okay, these two graphs are reflections. So I'm really reflecting f of x over the x-axis. That's how I'm getting to g of x. Okay, I'm really kind of negating the y's, which really means I'm reflecting it over the x-axis. Okay, so I'm going to let you look at these next two. Try number 8. Okay, I want you to fill in the table. I actually already have it filled in. And I'm going to let you try to find 8a to find the domain of that. Okay, sketching those graphs. Okay, so take a few minutes and try those. I've just sketched each and looking at the relationship. The 3 minus x opens to the left and the other one opens to the right. Okay, one of them is increasing and one of them is a decreasing, right? This one right here, h of x, is a decreasing one, where increasing, do we call them both h of x? Sorry about that, let me fix that. This one is actually f, I think, yeah. I labeled that wrong. That should have been f up there. Sorry about that. And the h of x, the one in red, is an increasing one. Okay, so I want you to try this next one. Try to come up with a domain for number 9. And then they're having you sketch it by hand. I did show you the work. Okay, so I filled in the table to find the x-intercepts. Okay, or to find the table of values so that you can graph this one. And then I have the graph below. So I want you to go back and do these parts right here and fill them in. And make sure you fill in the graph. Okay, and the next one here, these are also just more examples. I'm not going to have you do everything, but this is having you finish up that other one on graphing that one you were just looking at. I don't want you to worry about this. I'm going to cross this part out, okay? And likewise, I'm going to flip the slide really quick because I want to do this. Some of these things we just don't cover. So I don't want you to do this whole activity. The only thing I want you to take away from that is the main thing they're trying to point out is if I have something like this, a binomial underneath a radical like that, I'm not able to split that up. Okay? It's not the same what I did with that fraction before, because that fraction was all one term. So in general, you can't split up a radical like that. And I'm going to skip over to your, is one more, oh, here, we got it. And you'll see right there, I think it's actually on the slide before, but if I switch back to that other slide, it's going to mess up the video. But look at the page 550 in the first part of the summary, you'll see that rule we just on number 6, that you're not able to split up a radical like this. And then this part of the summary, we'll just go through talking about the domain that we just talked about keeping that radicand, that term under the radical, keeping it positive. Okay, so give those a try. Fill in the ones that I had asked you to fill in, but then the ones that I put an X through, don't worry about those.